we learnt about how one band is going to be a line, and then as the satellite moves, the next line is taken, the next line is taken, and so on, right. So, in that line there might be many detectors, some based on the number of pixels in the width of the image. Suppose you have 10 pixels and then the fourth pixel is not working, the fourth detector is not working. So, over there it will give 0 value, everywhere else it will be giving some value, correct. Now, that is for one line. When it goes to the next line, then that is also going to be 0 for the fourth line, fourth pixel. So, fourth column will be black and all others will be proper, the data, right. Have you understood? Okay. So, that is because the pixels, the detector is in the form of a line detector. If it is having the width of the detector is 10 pixels and the fourth pixel is not working, and the fourth pixel will not work not just for that line, but the next line and the next line and all the lines. So, if you look at the image, it will look like one entire column is missing. So, that missing column, to correct for that, we will take the column on the left side and the column on the right side and take the average of that. Okay. So, that is what is meant by bad column interpolation. We are replacing the bad values, the 0 values over there, with a rough estimate of what it could be from the nearest pixels. Okay, yeah, no problem. You all have done? That is the exact same. Yeah, no problem. Any other doubts? Something is there? You have any? Okay. Yeah. Fine. Okay. So, for working with hyperspectral data, limited level of processing can be done with other softwares, like if you have used QGIS, that is an open source software. With that, some small things can be done. Even with ArcGIS also some things can be done, and NV though was one of the first to start with a very good spectral processing. So, initially they came out with this, and subsequently others also started to bring in many aspects of NV into their programs, like what NV is doing for the spectral processing, that was brought in by other softwares also. But using NV in this mode, it is the easiest to explain, so that is why I am using this. So, just watch and then take a look, because NV is a paid software. So, this is not really something which can be distributed, right. So, we will just show you the demo of the data. So, the data when you download for hyperspectral, I have done first level of processing of removal of all the bad column and the bad bands and all of that. Okay. So, this is the final data which has come to which is available. So, yeah. So, now let us see this data. Two data sets here. One is a multispectral data of a sensor called RapidEye, and another one is a data of Hyperion, which is available as a hyperspectral sensor. So, what you see over here is the wavelength it denotes. Okay. So, remember when we were looking at indices, I said because there are multiple, even when we were discussing outside, there are multiple shades of blue, right, all of them are of different wavelengths, no. So, this 426, 436, 447, all of them will be different shades of blue. So, you will be able to see them, they will be having a slightly different response. Now, if you can see for multispectral, how many bands are there? After 475 directly to 555, and then 658, 710, 805. From this if you see 400 to 555, how many bands are there? So many bands are there, right? Around 15 bands are there. So 15 bands are there in that range where only one band was there for multispectral. So in the same wavelength range, hyperspectral has more number of bands. Okay. Now let's take a look at the grayscale image. Let's load band. So this is the first band of rapid eye is going to be loaded. Okay. So it's something like this. Now I'm just going to create a new display for Hyperion and then load a band for this as well. So I am loading 548 for Hyperion. Yeah. Okay. So in order to see the same thing, we can, I think we can do this link displays. Okay, sorry, I think this is over two separate locations. That's funny. Maybe one of these data sets don't really have much of a geographic data, that could be why it's not able to link. Either way, let's just see how it looks over here. Okay, so let me just try one more. Okay, no, I don't, fine. Okay, so now it's linked, I guess. Based on the geographic location, it has linked. Okay, so tentative, roughly. So now let's take a look at the spectral response. Right click and go to Z profile. Z profile is basically telling you about the spectrum. What is the value of the pixel for each of those bands? So when you take a look at this, for rapid eye, you get something like this. For Hyperion, what happens? Okay, I think I did something. Okay, yeah. So what happens here? If I go to Z profile, anyone can guess what will come? See, there are a large number of bands over here. So what do you expect to come? Yeah, you will get very detailed spectral response, right? Okay. So you can see, this is the sort of spectral response that is going to be available. Sorry, this is a little okay. So the spectral response is coming like this. So do you see the difference over here? How many bands are there over here? 1, 2, 3, 4, 5. That is similar to the 1, 2, 3, 4, 5 over there, right? Over here, so many more bands are coming. And this is the wavelength mentioned, by the way. Remember, wavelength is mentioned over here. So that is popping up over here. So do you understand what is happening? Hyperspectral. in the range of 500 to 2000, almost 2400, 2300. This is a these many bands are available. Whereas in case of the multispectral data, the range is lower, yes, but then it's from 400 and something to 800, and only these many bands are there. Only 5 bands are there. Okay. So understood the difference between multispectral and hyperspectral now? For those who had doubts in this, it's fine. Next, let's see what are the processing steps that you need to do. So we will have to do some form. Hold on. So any sort of the band wise. Remember we had talked about the hyperspectral indices. So what do you do there? We have got band math, right? So band math. Oh, sorry, you all have not learned band math. So I should explain this once. You all have learned raster calculator. Not yet. Okay, fine. So if you want to do any sort of calculation on the bands, for example, we are saying NDVI is NIR band minus red band divided by NIR band plus red band. So NIR is one image, red is one image. You are doing subtraction for each of those, right? So to do that, we are going to be doing it with something called band math in case of ND. In case of ArcGIS, that same thing is called raster calculator. In case of QGIS also, it's called raster calculator. Various other softwares have different names. So this one is called band math. So click band math, and then you can write your expression here. So I am writing B1 minus B2 divided by B1 plus B2. Okay. So this add to list, okay, then click OK. Now we get to select which bands to be performing this operation on. So this we saw is a multispectral one. Let's see how to do a hyperspectral indexing. It's the same in case of multispectral also, you just choose the bands accordingly. Now remember we have multiple NIR and multiple red, right? So what did that paper say? We had seen 800 as NIR and 670 as red. So we will choose as close values to that as we can. 803 would be a good option for as close to 800, right? So 803 we will choose as B1, and then 670 was the other option asked, right? $671, it's fairly close. So for that, click on B2 and click 671. Now we can either output the result to memory or to file. If you are doing file, then that data will be saved as well. So then you can, I am just putting in desktop right now. Okay, okay, I will put it back into E drive then, huh? Now after this you can also put the extension, huh? So TIFF is a common extension to use. So now click OK, and then it will run that. So we have this band math expression B1 minus B2 divided by B1 plus B2 available. So this is NDVI, right? So let's take a look at how that looks. Let's load it into another display. Uh-oh. Uh-oh. So let's load it into a new display. Display 3, this one, load band. So then, uh-oh, what's happened here? Is there something wrong? This is band 3. I selected the same band over in both cases. I'll just try once more. Okay, let me just try once more. Yeah. I can do, did I give you a subset mesh? Let's just create a quick subset, huh? Okay, just take a pause for a minute to make the processing a little faster. I'll just create a quick subset. You can ignore what I'm doing, don't confuse yourself.
पलटना पड़ रहा है. This is the logic that we are repeating since first day, right? Every day you are studying about it. It is a thing which has been repeated every day. कुछ रिफ्लेक्टेंस जिसमें हाईएस्ट होता है, फिर इसमें लीस्ट होता है, ऐसा कुछ सुना था? Why do we use NIR and red band in NDVI?
When the light reflect, when the sunlight reflect, then the ground particles it is seen, it has been seen when it's green, it has been seen in light color. So for that reason,
Finally, yeah.
NIR and IR is applied in NDVI so that we can see,
Why NIR?
so that we so that we can see the for example, vegetation. If it's green, if the light reflects, then we can see in white. But if we use NIR and IR, we can see the vegetation in red in color and the water in deep color.
We'll discuss this later. Now focus on the screens.
Yeah. So the issue is when I was writing the formula, by default it treats it as an integer. So whatever values are there between 0 to 1, it will treat it only in integer form, right? So that's why it was required to convert it into a floating point, and so we have applied float, and then we have got the NDVI values over here. So the values can be seen by double clicking, and then you can see the values over here. All of this, whichever location is pointed over there, we will be able to get the values, correct? Now there are a few values over here which are negative. Why is it negative? Think. You will have the spectral reflectance curve, right? For vegetation, you've seen how it is. Okay, I'll not disturb over here. Wait, I can. So the spectral reflectance curve like this for vegetation, and then we had like this for water, correct? Right. So if this is how it is for vegetation, and this is NIR, this is red. Now what is NDVI? Who mentioned NDVI ka formula before? Think. Huh? Tell. Divided by NIR plus red. Perfect. Okay. So now for vegetation, what will it be? High NIR, assuming this is something like 0.7 and this is 0.1, this is 0. So for vegetation, what do you think it will be? 0.7 minus 0.1 divided by 0.7 plus 0.1, which will be equivalent to 0.75, right? It is right. 0.6 divided by 0.8. Maths, we can do this. 3 by 4, which is 0.75. Okay. Now for water, let's do for water, NDVI water. What is this value of NIR? What is it? Someone is saying 0.1, but then NIR we are considering first, right? NIR minus red. Red is somewhere close to 0.1, fine. NIR is 0. So 0 minus 0.1 divided by 0 plus 0.1, right? So it becomes minus 0.1 divided by 0.1. Will that become minus 1? Yeah. So negative values are for water. In case of NDVI, negative values will be for water because NIR values are less than red values. It might not be exactly 0, we have put 0 in this, it can be some very small value like 0.001, and then for red it will be 0.05 or something. So whenever you are doing that, it will be 0.001 minus 0.05, some negative value, right, because less value minus high value is negative, divided by the sum of those values, which is going to be positive. So negative divided by positive is negative, correct. So then we get this. Okay. So right here. So that's why these values here are negative. Though, and now can you tell me, based on what we saw about grayscale, why it is showing black here, white here? Remember grayscale? So what's happening? Lowest value or lowest set of values being given black, highest set of values given white, everything else shades of grey in between. That's what's being done over here. So what does that tell us? These are all white. That means they can be vegetation, exactly. High values of NDVI are for vegetation, negative values and very low values would be for water, and in between moderate values would be for other land cover types. Okay. Next, let's go to classification. So you all have learned classification yesterday, right? Practical also? Yes. Okay, fine. So for classification, what did you all do? You all have created some ROIs, right? And then you all would have applied some of the classification algorithms, no? ROIs meaning those training samples. You all have created a few pixels you have given for training.
That is signature file that you have
Signature file, yeah. The signature files that you have created, right? So those are a few example files given to the algorithm to tell us that this pixel, any pixel with these set of values is belonging to water. Any pixel with these set of values for the different bands belongs to vegetation. All of that are the example files. So they are called as signature files or ROI files. So these are different names in different softwares, that's all the same thing, okay. So we can create a few ROIs. So for creating ROIs, you can go to tools and region of interest, which is ROI, and then ROI tool. So I'm just closing, so this is an old ROI I have created, I'm just deleting. Oh, this was in the other image, right? right click does not work on any disk or something? Should work, no? Okay, fine. Yeah, oh, okay, it's no problem, we can do from here. I think there's a bit of a delay. Okay. So here we can just come over here and we will create it from the zoom window. So this is water we have seen through the NDVI values, right? So I am giving it as a few example pixels. So this is water. You all have done the same thing in ArcGIS or QGIS yesterday? Yeah? You all have done. Which software did you use? AirDAS. Okay, fine. But you all have created like this only, right? You have created some point locations and then those are going to be extracted. Now, let's just do a simple 2-class case. So now we have 2 ROIs. For classification, we go into supervised, and then you all have seen last time about some of the classification techniques. So now these first few are a little preliminary. So for hyperspectral classification, we can go, the simplest one would be spectral angle mapper. Let's go with that. So we select the ROIs and then we click OK. Now we have got these 2 ROIs which are going to be used for the classification. We can also plot them. You can see the green ROI is having a spectrum something like this. Now let's just see for water how it looks. The spectrum is something downwards, right? We have seen it's all increasing, it's higher in the visible and going down in the NIR. That's why it's negative NDVI for water, right? So this is how it is. Okay. I'm setting this to none. Okay. So now we have the classified map. Oops. Yeah. So the green is not water, red is water. I'm not calling it vegetation because we've just created ROIs like that. So as per our requirement, suppose we are having a few ground truth points when we go to the field. Now, if you're working in say agriculture and you have a hyperspectral image of an agricultural field, and then in that field there are some locations where pest has attacked. So because of that the response will be a little bit bad, right? The spectral response will be a little different, no? So you go and mark those locations on the field. The geographic locations, I think you all will be learning that, or you all have learned that already. You mark those locations, you take those latitude, longitude, then you can right now we have created ROI. Instead of us creating ROI, we can take those we have taken from the field also, okay. So once we take those we have taken from the field, it will pop up like this, and that can be used for classification. So we'll be giving a few examples of those which have been affected by pest, a few which have not been affected by pest. Then from that image which we have captured, all other pixels of that image will be classified accordingly. So you will be able to classify your entire set of crops based on whether it has been attacked or no. Okay. So all of this is feasible with hyperspectral data because the spectral information is reflecting it. If the spectral information is not reflecting it, then it will become a problem, and that we won't be able to do. So that is what will happen if you were to use multispectral images instead. Okay. So this is about classification. Now apart from that, any other tools to show you for denoising? We use this MNF or PCA I mentioned, right? MNF or PCA. So you have to do the forward rotation and inverse rotation. This is that transformation which I mentioned. First you are transforming from x to x square, x and y to x square y square, and then from that you remove the noise, and then we are converting it back into x and y. So forward converts it into x square y square, and inverse converts it back from x square y square into x y. Alright, is this clear? Okay. So I am just showing that over here, and yeah. This has the atmospheric correction options. See over here, quick atmospheric correction and flash. Flash is that radiative transfer model based one we talked about. Quick atmospheric correction is the empirical one we talked about. So what does that do? It will convert from radiance to reflectance, okay, surface reflectance. The energy which is received at the sensor, it will correct for the effects of the atmosphere, and we will get the target reflectance directly. Okay. So this is what happens in case of atmospheric correction. Apart from that, there are a few other techniques also, but then these two are preferable to use. We also talked about spectral sharpening, right? We talked about spectral sharpening. Should I remind you? We have a very high resolution, high spatial resolution data, and we have high spectral resolution data. We merge it together, and then we get high spatial resolution, high spectral resolution. Okay, this is called spectral sharpening, and that can also be done under this spectral tab. All of these sharpening techniques can be used for that. So these are some of the things which can be done with hyperspectral data. You can also, well, yeah, that's pretty much it. I will not do more than that because it will confuse you. Can I show you any of the things again? If you would like to see any of the processing steps again, I will show that. We have some time right now. Let's do that. Yeah. Which one? It's okay. Ask freely. Which one? Okay, the full steps to be done, right? First things first, when we are starting with working with the data, I'll just remove all of this. So, how do we open the file? To open a file on NV, we go to File, Open Image File, and then we click on the file name and click open, it will open. So, that way we have opened these two files. Now, from this I have taken a smaller subset over here for showing you. That is why I am working on subset, otherwise you can do on this also. It is just that processing will take a little bit of time to run on each step, no. So, that is why I have taken only a small part and given as subset. No confusion about that, right. It is exactly this file, only one small part of it, okay. So, that is just for you all to see and understand. So, now I am closing this also. We have a file, any of these bands can be loaded as grayscale or color combination. Grayscale, you can click and then select whichever wavelength you want. Suppose your wavelength of interest is 599, you click and select load band, it will come. If you want to do a color combination, come to RGB and then set the color combination as you please. For example, if I put 800, 670 and 560, what do you think will happen? Is this going to be true color or false color? 800 is NIR, 670 is red and 500 and something is green. What is this, true color or false color? False color is correct. It can't be true color because NIR is being used over here. Humans can't see NIR, right? So, that is why it is false color. So, then let us load it and see how it looks. So, this is why, this is how it is appearing in the thing. So, all these red patches and the pinkish patches over there, those are vegetation. The black ones are water, right? Okay. So, now you have understood how to open the image, you have seen how to do visualization in grayscale and color composite of hyperspectral data, correct? Fine. Now, next step, it depends upon what you want to do. For some things, you can create hyperspectral indices. For that, we will be doing through band math. Oh, but before we go to band math, let us take a look at the spectral profile. Let us take a look at the spectral profile. Over here, if I click and right click, Z profile, then we will be able to see what the spectral profile looks like. Okay. Now, let us see for water. Something like this, fine. We are able to see the spectral profile of vegetation and water, all of that can be seen. Now, next we are going to be working with hyperspectral indices. Let us try that. Hyperspectral indices are done using band math. Band math and this was the formula we have used for NDVI. So, earlier I had made a mistake by putting just B1 minus B2 and putting a rough float about the entire thing. So, that will not really work because when you are doing this computation, it is treating each of those things as integers. So, to avoid treating them as integers, we need to treat them as floating point numbers, decimal numbers. So, decimal numbers are represented through float of B1 minus B2 divided by float of B1 plus B2. That was done. Okay. Click OK and then assign the band to B1 and B2. So in our case 800. For B1 and for B2 670, right? Now I'm saving to memory, click OK, and we have got that coming up in the list of bands here. Let's load it in a new display. Okay, so we have the display here. This is the NDVI values. So lower values water, higher values vegetation, correct? Okay. Now we have NDVI. We can also, if this is one possible step which you will do. Suppose you have got the data with you and this is the final process data, then you will be able to directly open it, visualize it in different color combinations, see the profile, the spectral profile, and do NDVI or whatever hyperspectral index you are using. You can use that and then see the output of that. Now, if you want to do classification instead of hyperspectral indicing, then you go to classification, supervised, and then choose your classification type. Let's try maximum likelihood this time. Okay, now choose the image over which you want to classify. Select OK. These are the regions of interest which we have defined already, right? So if you are uploading the regions of interest, those will come. Others, if you are creating those regions of interest, these will come here. So select all, then memory, no. Okay. All right. So so this error has come. Actually, this is a good demonstration of why those earlier classification techniques will not work, because we mentioned we need larger number of points. The error which came, you saw the error, right? I will show you again. Just take a look at the error. You must have these many bands plus 1 points for each ROI. So in our ROI which we have created, we have 101 points, 111 points, but the number of bands is more than that. So that's what we were mentioning. Regular classification techniques for multispectral, when we are doing, we'll be having only a few points also, we'll be able to work with it because the number of bands is very few. But then in case of this, because the number of bands is so high, that's why we need a large number of ground truth points. Okay. So now we won't be able to work with this, we'll have to work with slightly better classification algorithms. So we can go with maybe spectral angle mapper or SID, any of those others can be used. These bottom, not binary encoding, these two or these two can be used. Okay. Now let's go with this subset, click OK. Now import ROIs. So this, because I have created our ROIs, we are doing from input file. If we have ROIs generated from field, we will be doing from other file. Okay. Right now we are just going with this. Select all items, click OK, select all, apply. here we are setting just where we are putting the outputs and everything, and yeah. New display band. So we have the displayed classified map over here. So now what have we seen? Opening the file, visualization in grayscale and false color. We saw how to create the band math expression and do a hyperspectral index, right? Next, we have also seen classification. Okay, so these are the 4 steps which are generally used in hyperspectral analysis. All right. Apart from that, if you want to do some form of sharpening or any other things, then that can be done with under the spectral tab. Spectral, if your image has not been corrected for atmospheric correction, then go for quick atmospheric correction or flash. If you have to do any of the other yeah, this is also available, quick atmospheric correction or flash. Yeah, sorry, if you want to do the spectral sharpening, over here you will find the spectral sharpening options. Okay. So yeah, these are the steps associated with hyperspectral remote sensing. Any doubts? Any doubts? Anything you want me to show again? Oh, any of you guys from here? What about you guys? Something you're having a doubt? You can ask, no worries. Yeah. Huh? The steps? Okay. The steps, for first one would be open the file, then would be to visualize it either in grayscale or colors, the color combination. Then we will be seeing the spectral profile. Then we can create the hyperspectral indices. For hyperspectral indices, when you're creating, you have to go to basic tools, band math, and then write down the expression that you need. To be doing NDVI, then you have to use the expression we have used. If you are going to be using any other thing, then accordingly you will have to do, like if it is a band ratio, NIR minus red, if you, divided by red if you want to do, then do float of B1 divided by float of B2 and then press enter. B1 you assign 800, B2 you assign 670, and then you will get that ratio. Any other thing you will have to just do B1, B2 accordingly, just assign B1 and B2 to the wavelength of your interest. Okay. Then, sorry, yeah, NV, yeah. Then after that, if you are going to be, you will be getting the hyperspectral thing. Then if you want to do classification, you will first need the ROIs. So you can create ROIs using tools, ROI tool, tools, region of interest, ROI tool. Okay. Here also you can do one thing. If you're having the location values from the field, right, you can also go to okay, no, not from here, it's from the other location only. So yeah, this is the ROI tool. So with ROI tool, we will be creating the ROIs over the image, and then we will be able to use that for classification. Float, oh yeah, sorry. Float is actually used for representing decimal numbers. For representing numbers like 1, 2, 3, that will be integers. 1.1, 1.2, even 1.0, all of those decimal after this point that it comes, that is going to be, that has to be represented in floating point numbers. Yeah. All right. So, yeah, once you go to ROI tool, you can also, if you have ROIs saved from before or in some other location, then you can restore ROIs from there, and then those files will be like something .roi is the format. So that can be used directly over here. Okay. So now we have the ROIs, then we can go to classification and then supervised and then go for any classification technique of your choice. You have to give the image, you have to give the ROIs and then you have to click classify. That's it. So that is the broad steps that you will be using. Fine, is this clear? Okay. Anyone has any? ROI is the training, the signature file you have created, right? So it is only those to give the algorithm an idea of these pixels. All the pixels within this belongs to this class. All the pixels within another thing belongs to another class. So, I'll explain this with paint, I guess. Suppose you have an image and you are saying you don't know this, but then these are they are having in the real world. I am telling you true. This is vegetation, this is water, this is barren land. So this is known to you in the true case. Now we have a satellite image of this location. The satellite image, when you are going to visualize it, it's with the number of bands and other things, right? So we don't know from just the satellite image whether it is vegetation or barren or anything of that sort. We are able to interpret it, sure, but then we can't directly give it to a user who does not know, right? So they will not be able to see and understand. So for us to give them, we have to give them something which looks like this, which tells that this is vegetation, this is barren, this is water. This is called a land use land cover map. This is easily interpreted by the user. Satellite data that we get cannot be interpreted unless you have some expertise in this, correct? Now satellite data, we are doing classification by taking one pixel, a few example pixels. Now a few, so this satellite data is of the same location, okay? And now we are taking a few example pixels and few example pixels here and a few example pixels here. What does these example pixels tell us? This is a few example pixels of vegetation, few example pixels of water and few example pixels of barren areas. This is taken from the satellite data. So if there are 10 bands in the satellite data, one pixel will be having 10 values, right? Now if you are giving this to the algorithm and saying that these are a few example pixels, if a new pixel comes, say from here, then it will check whether it is similar to this pixel, this pixel, this pixel, or this or this. Whichever one it is most similar to. For example, if the pixel values of the new pixel is most close to the pixel values of this pixel, right? So then we will say whatever class this is from, this new pixel is also from that class. So that is called classification. That is what the algorithm is doing. It's checking the similarity of a new pixel with other known examples. ROIs are for creating those known examples and feeding it to the algorithm. Without giving those known examples, we don't have anything to check the similarity with, right? So that's how it is. Yeah. Anyone has any doubts apart from that? Is this clear? This part is clear, right? Classification. Anyone? Okay. If that's the case, then I think we're done with hyperspectral lecture. We'll do the microwave in the afternoon. Yeah, no worries. If you all have any doubts at all, let's discuss.
You can ask doubts from previous lectures also. You will
Yeah. No problem at all. You can ask away. Ask. Yeah. Google Earth or something. Sorry. Okay, so generally all of these sort of things, the example pixels and everything, we go to field only and collect it, because when we go to field we get the absolute true representation of what is there on the ground. If it's absolutely not possible to go to field, then we will be able to do it through some very high resolution image. Like if you are going to Google Earth and then seeing how it is appearing. Access? Yeah, so that becomes a problem. Yeah, use this, no worries. Yeah, some higher resolution images become a bit problematic. Most of the time again we go to field. If we are unable to do that, then the best resolution that we can get. Google Earth will give you historical time scale images, but then that is not always ideal to use because we might not get for the month of our interest or the exact dates of our interest. So if you have the funds, you can purchase high resolution images either from private players, or even Indian satellite data becomes a little bit cheaper, so we can use that. So that can be done. Alternately, up to 10 meters we are able to get sentinel data. So that one is the worst case option if you're not able to do any other. But then that is always, it's always preferable to go to field. And when it comes to other data sets like vector files, which administrative boundaries and all of that, it's always good to go for data sets which are published from government sources. So if it's published from government sources, we have the authenticity and we can say that we can give that reference that it has been done in this way, it's available to all public and there is a reputable source that way. Okay.
And then we can prefer like going to government and collecting the particular data.
Yeah, that can be done. Some government portals are also there. For example, if you've seen that's what I do.
Bhuvan portal.
You all have seen Bhuvan?
Yes, ma'am.
Okay, and you all have seen Bhunadi?
No, ma'am.
This is also another place where you'll be able to order satellite data. This is for browsing and ordering satellite data, Indian satellite data, okay. Apart from that, for the Northeast specific, we have a few portals available at NESAC. So one is nesdr. So this is Northeastern Spatial Data Repository, and most of the spatial data that you would require in the form of land use, land cover maps and everything can be ordered from here. It's typically given free of charge. You just have to create a login ID, or like by registering, click register, create your login ID, and then you can search for the data sets over here like land use. So this is Manipur land use, land cover, Assam land use, land cover. So this land use, land cover map can easily be
Ma'am, we can
downloaded.
assess district wise too.
Yeah, district wise also can be done. They also have another portal called NEDRP. Yeah. So this gives district wise resources. But then this one, all the data that is there over here is also available in NESDR, and this is updated more frequently. So it's preferable to take this, and then you can download the district boundaries like district boundaries are here. So if you just search for district boundary, you will get all of them. So once you download this data, you will be able to clip as per the district that you require. Okay. Yeah. All right. So
It's free.
yeah, it's most of the data is free.
Okay, ma'am.
If you create a register, you have to register for this account, okay?
Ma'am, from this portal, if we download the map, we can use in what is it, QGIS too.
Yeah, it will be feasible.
Okay.
Yeah, all right. Any other doubts?
संजय भैया और शायद वो वही आ रहे हैं
UAV. Okay, any other doubts? Any other data sources you all would like to find out, or anything else pertaining to what project work you would have and the role of remote sensing GIS to that?
you can contact her for QGIS also.
Oh yeah,
She is one of the expert in QGIS.
hardly.
Not
Yeah,
hardly.
yeah. I
have
mean,
learnt
we
a lot from her in QGIS.
QGIS is an open source platform, so you can work with you're using, right? Yeah. So most of the new QGIS version 3 and upwards, they are having a lot of new tools which even ArcGIS is not having. So the open source platform has really come together and provided a really good product. So if you'd like to use that, that's also pretty cool. Everything that we did over here, band math and everything, all of that can be done in QGIS too. Even classification, the simpler tools are, I mean, simpler algorithms are available very easily. If you're going to go for better classification techniques, there are some additional toolboxes that you can download. There's something called Orfeo toolbox, which will allow us to use hyperspectral classification also. So that is an option.
We can give you the handout.
Yeah. I have handouts for those. I'll email it to you maybe by tomorrow when I'm back home. I can email it. Sorry, I'll be back on Monday, so I'll email it. Yeah. Yeah. Yeah, 3.10. Huh. Yeah. It is already. It gets migrated. Most of them. Yeah. Some of the version 2 tools might not get migrated. Only some of them, but then most of the other tools are updated. Anyone else? Okay. In that case, I think we can break.
For the lunch.